The structure of the talk will be as follows. I'll begin and describe in a few words the low-Reynolds number of fluid structural interactions and the governing dynamics. Then I will present soft robotics and show how fluid mechanics interacts with soft robotics. Then I would present initially a simplified model of simply flow through an axisymmetric shell to see how we can create and control deformation by interaction between viscosity and elasticity. And in part two, I'll present a more realistic configuration of an elastic, slender elastic beam with an embedded channel network, which is deformed by the stress applied by the fluid. In the last part, I'll present some ongoing unpublished subjects and ideas that I'm working on. Okay, so let's assume you have a problem that you're studying, and this problem involves a fluidic domain and a solid domain. All of the configurations are governed by conservation of mass and Cauchy momentum equation. And if you have a fluid, and assuming it is a Newtonian fluid, you'll substitute the Newtonian constitutive relation and get an Navier-Stokes equation. If you have a solid, assuming it's a Hookean solid, you'll substitute the Hookean constitutive relation and you get the Cauchy-Navier equation. So it is clear that for solids, the stress is a function of the deformation, while for fluids, it's a function of the velocity, which is the time derivative of the deformation, and thus we get a new time scale. Viscous elastic time scale, which is proportional to the ratio of the viscosity of the fluid and elasticity of the solid. This time scale defines the viscous elastic transient dynamics, and in general these problems are governed by some sort of parabolic diffusion equations. It's interesting to know that you can get in these systems very fast creeping flows. You can see here the relevant Wormsley number. So if you have a very viscous liquid and a very stiff structure, viscous elastic dynamics can be in fact very fast while still keeping creeping flow. Viscous elastic dynamics is relevant to many fields of research. The two most prominent ones are microswimmers as well as blood flows. There are other studies in biomechanics. There are also studies about interaction of an elastic film with a rigid surface, which are both connected by a thin liquid layer. And you can see here an application to the dynamics of wrinkles, elastic peeling problem when you try to separate an elastic sheet from a rigid surface, as well as geophysical gravity currents, which are maybe very different but are described by very similar mathematics. There are other subjects and other works that I don't mention here, of course, but here we'll focus on soft robotics. So the first works on soft robotics were done by a Japanese group headed by Suzumori in the early 90s. They actually did very nice experimental results, and these actuators are operated by pressurized fluid, but it didn't catch. And there was no interest in this field until a few years ago, where Whiteside started working on the subject. So you can see here, I think it's the first work by Whiteside showing a soft robot overcoming some obstacle. This is a more recent work by Whiteside's group, where you have a soft octopus-like structure with complex interconnected channels and chambers, and actuation is done by a chemical response which increases the pressure of the fluid, thus deforming the solid. The field of soft robotics promises maybe the opportunity to create robots which have a superior obstacle negotiation. You can see here the amazing thing that this octopus do. So soft robots may have some of these abilities. Also, specifically if you're talking about fluid-based soft robot, you can achieve complex deformation patterns by actuation really in some kind of a localized location, and you can create complex deformation with simple actuation. Also, the simple fact that it is a soft allows to manipulate delicate cargo and also to directly interact with humans. And in general, currently, this is a very, very active field. A note, in this talk I will talk only about fluid-based soft robots, but there are other methods. Maybe the most common one is shape memory alloys, but we will not focus on this. We will focus on fluid-based soft robotics, and in general they are constructed of some kind of a combination of internal cavities and channels which are connected, and are pressurized or actuated by some sort of a syringe or pump or chemical response, and deform the surrounding solids. And when you look on this, the question is, how would you model this? So here we have a rigid soft robot, and this is a very, I guess it's not simple to model this thing, but still you have a finite number of degrees of freedom. You can build a matrix and so on. But how would you model a soft robot? How would you model a soft robot actuated by internal fluids with inertia, etc.? This is a bit more complex, and this would be basically the goal. This is the goal of this project, to model viscous elastic interaction and try to get new ideas and make a better soft robot. So I'll start with the simplest possible configuration. So just flow through an axial slender geometry. So we have an internal rigid cylinder which may move relatively to an elastic external shell. And we introduce fluid into the gap between the rigid cylinder and the elastic shell. And the first, so this is already a significant simplification. We can further simplify this by assuming that the deformations created by the flow are small compared with the initial thickness of the fluid layer between the rigid inner cylinder and the external elastic shell. This ratio is described by lambda h here, which is H0 divided by dr star. H0 is the initial gap, dr star is the deformation that we create. In this limit, we linearize the problem and we'll get a linear diffusion equation. This is not which can be solved, and we'll obtain the deformation dynamics. This is not what I'll talk about today. I'll talk about the opposite limit, where the deformations are much, much greater than the initial gap. In this case, we have a nonlinear interaction, and if we can look on the governing equations to see where it gets us. So the evolution equation of the fluid is described by this relation, where dr is the radial deformation, p is fluidic pressure, lambda h is the ratio between the initial gap and the characteristic deformation, and uh is relative velocity in the axial direction between the body and the cylinder. We also have an elastic equation which comes from the thin shell approximation, where here we can see this term is related to elastic bending, and it's multiplied by a very small number. And this suggests the existence of an inner region and an outer region. So we can solve for the inner region, and we get this equation. This is a porous medium equation, and it allows exact solution by self-similarity. And this solution is presented here, and this solution, you can see here the plus sign, meaning that when z is equal zf, zf is the location of a discrete front, a compactly supported front, p is 0. So there is a discontinuity, and this discontinuity would obviously create a boundary layer to correct the infinite jump in dr, in the derivative of dr. So we can solve also the inner region, and we can then connect them asymptotically, get a uniform asymptotic solution, which basically describes the front. And we can see here the outer solution, the inner solution, And this is the uniform solution, and we have a moving boundary layer which propagates as the fluid propagates into the elastic cylinder. We can also solve for intermediate values of lambda h, meaning that the deformation is not very large or very small compared with the initial gap. In this case, we don't have exact solutions. We still have, though, self-similarity, and we can solve an ODE numerically, and we can see here that as lambda h increases, the discontinuity of the front vanishes, and eventually there will be no boundary layer. So this would be a sufficient regularization. Okay, so we can now maybe try to use this to design deformations. So if we look on the characteristic time scale, T star, it is inversely proportional to the characteristic pressure to the times of 3. So if we have advection in the system, if we have relative motion, we can basically create impulses moving within the system and separate them by regions of very small gauge pressure. The very small gauge pressure will create very large timescale, and basically information will not be transferred through the different pockets. And this allows us to create this kind of basically signals of the formation propagating. So let's try to model a more realistic configuration. So software robots don't really look like a cylinder. And here I'll talk about an elastic beam. So this is a slender elastic beam, and it has its own coordinate system, ZS, XS, YS, and within it there is a serpentine slender fluid filled channel. The coordinate of this channel is XC. This is the streamwise direction. And due to some asymmetry, when you pressurize the channel, you create deformation of the elastic beam. Okay, and we can get the effect of a single beam by numerics or experiments, and then can use long wave approximation and obtain an induced curvature of the beam as a function of the density of the channels and the effect of a single channel, which is related to the pressure within the channel. We can then write the 3 equations governing the problem. The first is the evolution equation. In this case, this is small deformation limits of the evolution equation. And so A1 is the area, the area of the cross section, and Q1 is viscous resistance. We can also write the modified Euler-Bernoulli equation, where here we have an additional term which corresponds to the deformation of deformation by the embedded fluid. And we also need a third equation, which is simply a conversion of coordinates from the beam coordinate to the streamwise coordinate of the fluid. We can combine these entire 3 equations and get a 4th-order linear partial integral differential equation. And we can solve this equation for various cases and try to understand what the dynamics of the system would be, and try to design the formation patterns. So if we're talking on the limit of negligible solid inertia and uniform distribution of channels, so the channel properties are constant, we can solve for a step inlet, for example, and see that initially the deformation is limited to a small area near the front. We can also see that actuation by a sinus with a period which is much larger than the viscous elastic timescale would create in the formation of the entire beam, where actuation by a periodic sinus with a period, that is much smaller than the viscous elastic timescale would create only part of the deformation. We can also create a standing wave without inertia. There is no inertia in this case in the solid, or a moving wave, etc. So we can use this to design what kind of deformations we want. The results were also validated by experiments, as you can see here, and they're also validated by 3D CFD. Okay, so now I would talk about a subject that I currently work on in my group. And the first thing is the immediate continuation of this published work. So we want to model a dynamic locomotion of a soft robot, which is composed of two legs. I don't have time for this. I'm sorry. So basically, we need to include axial forces acting on the legs, and we're currently working on modeling two soft actuators trying to run with dynamics and inertia and contact with the floor, etc. Another idea is to use viscous peeling to create a simpler soft robot. So earlier I showed you the characteristic way to make soft robots, right? You need to create a structure with complex internal cavities. And then you need to fill these cavities with liquid or air and try to actuate them. But you can also do something much, much simpler. You can just print an internal structure. In this case, we printed a serpentine channel. And then we immerse this in some sort of a polymer, let's say PDMS, and then we get this composite structure. So you have an internal solid material contained within an external soft material. Now, actuation can be created simply by introducing of flow in the interface between the two solids, and that's much significantly simplifying the fabrication. You can also see here beautifully the propagation front. Okay, so this is what we saw in the peeling problem in part 1. Another problem is to study large deformations of such structures, which requires to use a Coserag model, and also involve creation of pressure within the channels by external forces acting on the solid, which also needs to be modeled. We are also trying to apply the same idea from soft robotics to soft wings. So it's within the field of aerodynamics, it's creating a wing that deforms continuously, significantly reduces the drag and allows better performance. But the problem here is that we need to do soft actuation, which is very light. The last subject that I will talk about is to use elastic bistabilities as an idea to control the formation of a complex soft robot. So let's assume that the different actuators are just balloons. So we have 3 balloons, and these balloons are connected by rigid channels for this case. And some material have this following constitutive relation between the pressure and the radius. So initially we have a Hookean relation, then we have a maximum, and then we have, due to material nonlinearities, we have enhanced rigidity again. So you can see that if you're operating for a pressure of 35, for example, you have 3 points. The middle point is unstable, so basically you have 2 possible solutions of these systems. And here we show that by applying a certain signal at the inlet, we can make, so the blue one is the radius of sphere 1, the red is radius of sphere 2, and yellow is sphere 3. So we can initially inflate the first balloon, then the second balloon, and then deflate only the first balloon. And then we can just choose which kind of which part of the robot we want to inflate. So this is for free. We're just now trying to do it for n balloons and basically get n degrees of freedoms from a single actuator. And that's it. So basically, viscous elastic dynamics allows us to, in modeling of viscous elastic dynamics, allows us to better control the deformations created in soft robots, and introduction of fluid dynamics to soft robotics hopefully is a subject that is open to new ideas, and that's it. Thank you.
We have time for a couple of questions while maybe James plugs his computer. Actually, I had a couple of, well, in your system with the serpentine, how do you, I did not understand how do you introduce the fluid?
You mean here?
Yeah.
So, so there is a lure connector. Actually, I don't know. A student does.
Okay.
But you need to create a tube that would come out of the rectangular beam, and then you need to create a certain connection between and outside the material. So you don't connect the tube to the rigid part, but to the soft part, and then pressurization peels the two solids from each other.
And if you imagine having such, well, so what does the role of the serpentine play? Like, does it have an important mechanical role, or does it?
Well, we need there is an asymmetry in the location of the channels compared to the neutral plane.
Okay, so that's
so you need otherwise it will not
but
bend.
if you are able to make like empty channels inside the polymer, it should be.
Yes.
Okay.
Yes.
That's a trick to make the channel.
Yes.
Okay. Yes. Okay.
Quick question.
Okay.
Maybe you said this, but just very nice. In terms of practically making a self-contained autonomous robot, where does one, or how does one actuate? Where do you supply?
Well, so actually, this might be a benefit of viscous spilling, because usually they use gas, and when you use gas, you cannot use syringe because you need to introduce much the volume of the network times something. But if you go to solid, to liquid, and this you can do here because you don't have to worry for in viscous spilling you don't have to worry regarding bubbles. You just need to actuate syringe. But in general, yes, this is of course a problem. Definitely in gas, less in fluids.
But incompressible fluid, you say, has some advantage.
Yes, because you only need to introduce the amount of fluid you need to inflate the channel.
Okay, thank you again very much.